we are going to discuss about the lesson learned from the failure of the bridges or components. Now, one very moot questions before us: how prosperity can be increased while reducing dependencies on primary material and energy? We have the limited resources. Everything is limited, but how we can increase that thing? So part of answer is applying the following concept: restorative by design, efficiently using the and reusing natural capital, finding value throughout the life cycle. If we go into the detail of this, we can say it is not just avoiding failure. We have to regenerate the systems. Each failed bridge is a missed opportunity to heal. The next can model how infrastructure serve both people and the planet. What I mean to say that we need to learn. Second point, we can say beyond prevention towards resilient, resource conscious design. Analyzing failure support a transition to sustainable infrastructure grounded in an efficient use and reuse of the natural capital. This includes whether we can strengthen the bridge, whether we can upgrade the bridge, because failure does not mean it has to collapse. Failure means if a bridge or any structure is become unserviceable due to change in the criteria or due to change in the load, then we need to do some other action and make it usable. Third item can be failure as a feedback loop for life cycle optimization. Insights from the failure optimize every life cycle phase, unlocking technical, economical, environmental, and educational values. So we have to learn from the failure and prevent it, and again learn from the future, and then keep doing in the cycle at every stage of the working. And now let us dive into the, I again request to mute. This action has to be prompt. Now, lesson from the bridge failure may be treated as a learning experience, because when the bridge collapses, it has certainly been pushed to the limit in some way. Now, deficiencies that may be found in bridges are numerous. This is including uncertainty in the load carrying capacity. There are examples where, because of inadequate estimation of the load, bridge has been failed. Damage to bridge member due to accidents. These accidents can happen when the bridge is in service or when the bridge is being constructed or erected. Excessive loss of the member cross-sectional area due to corrosion. We have example where there has been loss of life and collapse of the bridge due to corrosion, etc. Several examples are there. Inadequate geometric clearances. Depending upon the dimension of the moving vehicle, what we fondly call moving dimensions, if there is any infringement, there are possibility of bridge failure or at least failure of a member or hitting or some loss of life. Another reason could be foundation deficiencies. It all relate with the estimation of the scour index, type of the foundation, what is the estimation of the water, channel width. So many things are coming. So they are one of the regions. Now, if you remember, last year we had several bridge collapse, several bridge failures almost during the entire monsoon season. And this year also it has started from one bridge failed somewhere in the Uttar Pradesh for the slab due to concrete collapse very recently, few days back. Now, options available for addressing the problem associated with the deficient bridge, including both rehabilitation and replacement. So we need to think that is what the regenerative. Unfortunately, in India, we are shy of doing analysis related to the bridge failure. We are very shy of cataloging it. But in US, they had made lot of studies, and I had been forced to take the example of those studies from the US. The Semi Thiel et al., they had made one study in 2001, and they find out nearly 40% of the bridges in US are structurally or geometrically deficient. Just imagine, in US 40% bridges are there. Some of the efficient bridges are in service with the speed and or load restrictions, and some are out of service. Another study done in 2012 shows that on an average, one bridge every month has failed during 2010 to 2012 in US. See, US has become a developed economy long back. They have a long history of making the bridges or infrastructures in their country. And because of that, the age of the bridge is quite substantial. That is one of the reason for this type of failure. So, and we are also now approaching to that level. In the past, a number of steel truss bridges has failed during various stages of construction or in service. The failure have been partial or total collapse has been taken place. The most common cause of the bridge failure, particularly truss, design defects and deficiencies, failure during construction due to lack of proper supervision or some construction mistakes. So again, it has come back to the design deficiency and construction inefficiency. Failure of the bridges can also be due to long-term fatigue and fracture, over-stress of structural elements, accidental impact from ship or the moving vehicle below the bridge in case of ROB, earthquake, lack of inspections, and unforeseen events. Again, if you look for the truss bridges, then the most happening failure are due to failure of the gusset plate connecting the member of a truss and buckling failure of compression member. Again, one analysis from the US, out of 347 bridge failure case studies they have done for a vast period of say 600 years, 10% bridges failed due to overloading. Out of 164 failed metallic bridges, case studies of 87 bridges were classified as collapse, and the most frequent encounter mode of failure are scour of pile or pier or foundation, buckling, fatigue, impact, and fractures. You can see that foundation failure is roughly 17%, buckling is 16%, fatigue is 13%, impact is 13%, and fracture is 9%. This is roughly around 70%. Still 30% there can be other reasons, but they may be numerous. Another analysis, out of more than 6 lakhs bridges in US, more than 1,000 bridges failed during 1980 to 2012, out of which 29% are truss bridge failure. So why so much emphasis I am giving on truss every time? We can say whenever it is becoming a steel structure having a larger span, we invariably go for a truss. That is why we have to be very, very careful about truss. Now let's talk about few case studies, historical case studies that are relevant. One is the Silver Bridge in US. It has failed at the age of 41 years. It is a suspension bridge. The bridge is having a suspension. This is the suspension cable, and it is a big span, around 700 feet. Right now, this is the collapse picture of the suspension bridge. Now, what happened in this? Here in the suspension, you are going to suspend the wire with some arrangement having a key, one eye bar holding the tower and holding the suspended suspension wire or suspension cable. Now, once that failed, the catastrophic failure of a single I-bar in a suspension chain due to stress corrosion cracking. The biggest enemy of steel structure is corrosion. And when the steel is subjected to high tensile force, the corrosion extends beyond limit and the failure happen very fast. So rust in I-bar joint has caused the stress corrosion crack. Then fatigue failure. It combined with the fatigue because high stress and the low temperature in that region make the structure brittle, and the loading standard has keep on increasing over the year. So that is how the loading cycle increases and it combined with the fatigue problem. Another issue is that is related to the inspection that undetected internal flaw, just 0.1 inch deep, 2 mm or so. That crack was there at the I-bar location in the hole, and then finally from there it has been separated out and filled. Now what is the biggest problem is no redundancy. One member fail, one joint fail, the entire bridge collapsed. So we have to see that from the design point of view, it should be there should be built-in redundancy, so that if a member failed, other member is ready to take the load. Contributing factor, I can say the material fatigue, no redundancy, lack of regular inspection, and aging infrastructure. So we are somewhere coming that 41 year or so, we are already crossed that limit. Now lesson learned is that non-redundant design is required. Non-redundant design is vulnerable, so there has to be built-in redundancy. Routine non-destructive testing. Now for the aged bridge we have to do. Then inspection protocol is to be decided. When we are doing in NDT testing, what shall be the inspection protocols when we say there is a problem? And that has made US to create a national bridge inspection in somewhere in 2068. So fortunately in railway we have laid down inspection procedure, but when it comes to NDT, that is still to be laid down, and then we shall have a expert agencies available, they can do. Another example we can take of the Quebec bridge. It is a cantilever. It was perceived as a cantilever steel bridge. It collapsed in 1907. There was casualties. A second attempt was made, and again it had some problem, and there were 13 fatalities in that. And after that, the second attempt continued, and then it was completed in 1917. So you can say that 10 years it took. Now the most important aspect here, what I will say that the cross-sectional area of the member of the second attempt is 2 times of the first attempt. Now, interesting point here is that in the first attempt, it was our private affair. A consortium was formed having the various stakeholders. It was privately funded, partially government funded, privately controlled, but when the second attempt made, it was a purely government affair. The difference is that in the first attempt, they tried to economize to the extent that they estimated the lower self weight, they permitted abnormal high allowable stress, they ignored the distress sign in order to complete the bridge, and the designer has never been visited to the site. There was no system of proof checking. In fact, it was objected by the designer, saying that I will become subordinate, so no proof checking. Another thing happened very funny. In order to make a mark in the history, initially it was designed for 488 meter long bridge. Later it has been increased to 549 meters, so that it will be the longest bridge of that time. But while doing that, they have not accounted the increase in the self weight of the member. They have not accounted what will happen by increasing that 61 meter length of the bridge, and what is the stress and all other thing. So that all made a tremendous mistake. So copy paste of design and no process of proof checking, over economizing the sections, These are the main problems. And another issue here is that the warning signs, the distress signs at the sign reported by the worker at the site has been thoroughly ignored, saying that the engineers has taken decision and it is not to be worth looking at. Now, now I request to mute, please. The main distress sign was there out of plane bending of a bottom card. It was somewhere around 20 mm, and within 2 weeks it has been increased from 20 mm to 57 mm. First of all, this 20 mm out of plane bending, what has been told, it is like buckling. So that sign was neglected in the compression member, which has been increased as the structure has been built, and from it has been become from 20 mm to 57 mm, and finally it has been collapsed. Second problem is that the rivets in the transverse bracing began to shear off. As this buckling increases, the shearing of the rivet has been taken place. That has also been neglected. Then there has message been given to suspend the work, but that has been ignored because they wanted to do the work as fast as possible. And under pressure, the construction continued and then it collapsed. So 27th August, that message was there suspended, and 29th it collapsed. So it has not given much of the time. That is what it took, almost 87 to 1907 to construct. But in that, they were in the last moment, they were in so hurry that it has given a lot of the problem, and finally it collapsed. So what are the lessons learned? Underestimation of self weight, buckling of compression member was ignored, then overstressing because of increase in the span length, overstressing of several member was ignored. It has not been discovered actually. Later on, when it was pointed out, then there was no time to do anything and rectify all these things. Then why erection? Whatever the distress sign was there, that has been ignored. That means a precise instrumentation is required, so that you don't say that this is the alarm is being raised by unqualified persons. So if you do is instrumentation, you will not have the problem. There was no proof checking, so there has to be a third party proof checking system. Site visit by the designer and poor communication. See, in those days, communication is taking lot of time, and when the communication is coming through the various channel, like stepping from top to bottom or from bottom to top, it increases the speed of communication and action taken. So that may result in the fatalities and the collapse of the bridge also. Another quick example, after that I will close, I believe. Next speaker may be on the line. This is case in India. It is collapse of the Chaurus bridge. It is a road bridge, but interesting point here is that it is again a truss example. You see, it is a 3-span continuous bridge. Now, if you see this photograph where it has been collapsed, you see it has been lifted in this manner. So if you look at this location, from there it is having lifted, and if you look at this end, this is at the abutment, and there also the extreme end is in lifted condition. So what does it simply means? What happened when the load is applied here? It is having a deformed like this way. That means at the end there is no restraint is provided against the lifting of the end of the superstructure. Now, had it been visualized, or had it been taken a holistic view, how the structure will behave, this type of mistake will never happen when we are looking for a 3-span continuous bridge, because this is a very fundamental thing we can visualize. When the central span is loaded, ends will be lifted up. So what is the lesson we have to learn from here? A new continuous span base, it is necessary to adopt proper side to main span ratio. Side to main span ratio so that the self weight of the structure is enough to prevent any lifting at the end. At the same time, we have to arrange the arrangement with the bearing so that a lifting of the ends will be prevented. Then second item is buckling analysis is important for the cylinder steel member. Here we have seen that the top member here, U13 and U14, in between there is a member U13, U14 that has been failed because of the buckling. Now, as per the codal provision, the slenderness ratio is limited to 30, whereas available was 72. That means it was highly slender. So that need to be taken care of. Vibration of the bridge of the similar configuration was ignored. Before that, similar bridge was made. Before that, a similar bridge was made and it has reported there was lot of vibration in that bridge. So that bridge, no lesson has been learned and the design has not been reworked or checked and it has resulted in the failure. So warning sign is again ignored here. Construction sequence. If we go in this bridge and if you say here the construction was started in the middle, if we do construction somewhere here, slab construction, then it will add to the weight. If you do construction here again, it will add to the weight so that the structure will be more stable and the central span will be having less buckling forces. Anyhow, that construction sequence need to be defined in writing properly. Now, reversal of stresses. Whenever there is a continuous type of bridge, there will be reversal of stresses that need to be taken care of. Sometimes compression member will become tension or tension will become compression. And whenever members are crossing each other, they should not terminate short of the crossing point and joined by the gusset. Instead, they shall cross each other and having a gusset plate in between so that the member should be available complete. There will not be a termination in between. So here they had this type of joints. This location you can say the member are crossing and there they had made a short termination of the member and they are only jointed by the gusset plate and then this is again a possible hazard location. So with this, I will be closing the presentation. Next presentation will be from Mr. Sudhir, I believe from NFR, related to the failure of or the restoration activities from the flood hit areas. So I request all the participants to please raise your question or type your question in the chat box so that I can look into that and it will be answered subsequently.